In this video example, we would like to present an advanced design technique of OptiLayer software. It's called sensitivity-directed refinement. This technique allows us to obtain near quarter wave solutions with excellent spectral performances. These solutions are suitable mainly for monochromatic optical monitoring because it's possible to monitor large blocks of layers without changing the monitoring wavelength. This technique is good for machines that cannot deposit layers thinner than 15 nanometers with a good uniformity. This design method is appropriate to designing of broadband blocking filters, short and long pass filters, cold and hot mirrors, and the specific feature of this design method is that a good starting design is required. The main idea of this technique belongs to Dr. Ulf Brauneck from Shot Glass and is based on many years' experiences in thin film optics. At each step the most sensitive layer is released and OptiLayer optimizes the design with respect to the released layers. And the number of released layers is the main parameter of the algorithm. Let's consider one design example. It's designing of the blocking filter. We have two low transmittance zones, from 400 nanometers to 480 nanometers and from 680 nanometers to 806 nanometers, and one high transmittance zone, from 557 nanometers to 587 nanometers. Let's look how OptiLayer will deal with this complicated design problem. Let's start to specify our target. In this example, target has 656 spectral points and consists of 3 regions. We can look at it in preview mode. Here we can see 2 low transmittance zones and 1 high transmittance zone. In the first and third spectral ranges, transmittance should be less than 1%, and in high transmittance range, transmittance must be more than 99%. So, in this case we specify so-called range targets. So, we specified B, below, qualifier for low transmittance zones, and A, above for high transmittance zone. Then we load this target. After that we load substrate. This is B270 substrate, 2-layer materials, niobium pentoxide, as a high-index material, and silicon dioxide, as low-index material, and our starting design is a combination of 2 quarter wave stacks. The layers from 1 to 26 have optical thickness equal to 1.75 kWot, and layers from layer number 27 to layer number 46 have optical thickness equal to 1 kWot. So, finally we have 46 layers and control wavelengths is equal to 440 nanometers. Then we load this starting design, and this is its transmittance. We can also have a look at refractive index profile. We can see that first 26 layers have 1.65 kWot and other layers have optical thickness equal to 1 kWot. Of course, a choice of a good starting design is equation to an experienced optical coding engineer. We would like to pay your attention that in this example we work in diabetic scale. In many cases this scale is very convenient. We can switch between scales in context menu of evaluation window. We click right mouse button and choose axis option. In this tab we can choose here diabetic scale. Now we can start our sensitivity-directed refinement. It's here in synthesis menu, sensitivity-directed refinement option. And there we can choose how many layers we need to release on each iteration. We will release only 1 layer after each iteration. After that we press OK button and, in some seconds, we obtain already 0 merit function and excellent performance. We can have a look at our refractive index profile, and here we can see that many layers have a QWOT optical thickness. 1.75 quad and 1 QWOT. And only several layers have optical thicknesses different from QWOT. This design is quite convenient for deposition, especially if your deposition plant is equipped with monochromatic optical monitoring.